Alright guys, welcome to solving quadratics by finding roots. So we've talked about how to solve quadratic equations by factoring, but you don't always need to factor, and sometimes you can't factor. So we're going to be looking at examples where we can solve quadratics with square roots, but there are a couple other things that we have to look at first in order to use these square roots. So we won't see the solving part until about the last two slides. Okay, so a couple things just as a reminder. When you have the root of s, okay, this is called the radical. Okay, this guy is called the radical sign here. Radical or root sign, usually I prefer it as root sign. And s is obviously a variable, but you have to be careful when we talk about s and it's underneath the radical. We're talking about the radicand. That's the name of the number or whatever's under that root sign is called the radicand. Okay, so just be very careful of that and know these terms. This is a radical. When we're alone here, we call that the root or radical sign, and the number underneath is called that radicand. Okay. Two properties we have to look at when you take the square root of, just a root of a product, a times b, you can actually separate that into root a times root b. And that's going to be very important when we start to simplify these roots. And the quotient property here is if you take the root of a divided by b, it's the same thing as taking root a over root b. So these are two really important properties that we're going to look at today when we're solving these quadratics by finding roots. Okay, in our first example, we're going to simplify two roots. One that's going to be a product and one that's going to be a quotient. Okay, so the first one, we're going to simplify the square root of 80. And so what you want to do, if there's no number on the outside where the index is supposed to be, we call that a square root. So this is a square root. Now, if we can, the goal is to write one of our numbers, or both numbers, if we rearrange this product, as perfect squares if we can. That's the idea. So when you see the breakdown here in the next step, you see root 16 times root 5. Well, 80 is 16 times 5. And that's good. So root 16 times root 5. And notice how 16 is a perfect square. The 4 comes out and the root 5 stays under the radical sign or the root sign. So the square root of 80 simplifies to be 4 root 5. In part B, you see here we have root 6 times root 21. Neither are perfect squares, okay? But let's multiply them together. 6 times 21 underneath that same radical, or root sign, is 126. However, we can write 126 with a perfect square in it. Root 126 is equal to root 9 times root 14. So root 9 is 3 times root 14, and that's your answer. Okay? When we look at problem C here, you have root 4 over 81. So I broke up the radical and I made it root 4 over root 81. And both those are perfect squares. So the root 4 is 2 and root 81 is 9. So that simplifies to be 2/9. In our last example here, we have root 7 over root 16. So I broke up the radical sign again. However, in the numerator here, I couldn't simplify, so I don't leave it as a decimal, I just leave it as root 7 over 4. Okay, and the note on the bottom here is just to make sure that when you're multiplying or you're working with a quotient, try to make one of the factors, or both, be perfect squares if possible. That way that perfect square can come out of the root. The next thing we have to talk about is rationalizing the denominator. This is important when we get into calculus and we take limits that involve radicals. The big thing here is we're going to rationalize the denominator. What that means is if there's a root or a radical sign in the denominator, we're going to get rid of it. Okay? It doesn't make the problem any simpler. A lot of people I've asked, I don't really know why we do it. I can see in calculus why we do it, so we can help simplify and find limits. But in Algebra 2, I mean, using the rationalize the denominator doesn't make the problem look any easier. We're just really just getting the radical sign out of the denominator. So that's what you have to think about here. So there's three ways we can write these roots. Okay, if you see this form in the denominator, so if you look at your fraction and you see one of these three things, we're going to multiply the numerator and denominator by these three things. So for example, If I see a root b in the denominator, I'm going to multiply the top and the bottom of that fraction by root b. If I see a plus root b in the denominator, I'm going to multiply the top and the bottom by a minus root b. And if I see a minus root b in the denominator, I'm going to multiply the numerator and denominator by a plus root b. Now these are important when you multiply these together. If you multiply straight across, those are conjugates. Same term, different signs. Those are called conjugates. Well, when you multiply conjugates together, you get this pattern. It's actually that difference of two squares, okay? Pattern. So that's really key when you're simplifying this, if you have to multiply out, and you'll see that in the next couple slides. You'll see more of conjugates when we get into looking at complex numbers in this unit. Well, that was a good catch. All right, so in this example, let's simplify when we have root 5 over 2 and 3 over 7 plus root 2. So, simplifying this problem, I get root 5 over root 2. So, I look in my denominator, I see a root 2, so I multiply the top and bottom by root 2. Using our product property, I can multiply 5 times 2, and I get root 10. And root 2 times root 2 is root 4, which is just 2. So you have root 10 over 2. Okay? In part B here, I have 3 divided by 7 plus root 2. So the denominator 7 plus root 2, the conjugate would be 7 minus root 2, and that's what gets multiplied here. Okay, so you're going to multiply straight across, so you have 3 times the quantity, 7 minus root 2. The difference of two squares says just square each of these terms, which is what I've done here. So notice I left the numerator, and 7 squared is 49 minus root 2 squared is just 2. So the denominator becomes 47, and then I went ahead and distributed the 3. I get 21 minus 3 root 2. Okay? So that's how you simplify and rationalize the denominator. As soon as you get that radical out of the denominator, you've rationalized it. Okay, in the last two examples here, we're actually going to solve the quadratic equation. So the first one is x squared divided by 25 minus 6 equals negative 2. So when you're solving these, the whole goal, again, is to get x by itself. But I've got a subtraction of 6, and I've got dividing by 25. So we move the 6 over, and we add 6 to both sides, so you see a positive 4. X squared divided by 25, well, if you're dividing x squared by 25, to get rid of it, you multiply each side by 25. So you get x squared equals 100, 25 times 4. Another way to think of it is if you did proportions, x squared, okay, equals 25 times 4. You take the square root of both sides. In this case, we're going to keep that plus or minus 10. So that's our answer, plus or minus 10 there for x. And here is a little more complicated equation. So you have 3 times the quantity, x plus 2 squared plus 4 equals 13. Before I can square anything, I'm going to get rid of the 4 and I subtract from both sides, 4 from both sides. Then I have that 3 out front, so I divide everything by 3. I divide the left side by 3 and the right side by 3, and I'm left with this. Now there's nothing being added or subtracted, nothing being multiplied out front. Now I'll take the square root, because that's how you undo that square there. So I square root both sides, and I get plus or minus root 3, and I get x plus 2. So now x is free, and we have to get rid of the 2 by subtracting 2 from both sides, and you get x equals negative 2 plus or minus 3, plus or minus the square root of 3. So that's how we solve those quadratic equations using radicals. Notice how we didn't factor here. We didn't have that nice trinomial 3 terms, or like that difference of 2 squares pattern. So we can't always factor when we're trying to solve equations, and this is just another way using roots that can solve equations and get our zeros. In the last example here, last two examples, move that board a little bit. Okay, we have solve 3x squared plus 5 equals 41. So you could say, well, Mr. Bennett, I'm going to bring that 41 over, and I've got 3 terms I'm going to try to factor. Okay. That's a pretty large number, 3 times 41, right? You would be looking for a product of 3 times 41 that multiplies to be that and adds to be, well, to be 0. And it's not a perfect square. So that'd be hard to factor. It's not factorable. So let's look at using that square root idea. So I subtract 5 from both sides, and I'm left with 3x squared equals 36. I divide each side by 3, and I get 12. Now I have x squared by itself equals 12, so I square root both sides, and I get x equals plus or minus 12. 12 is 4 times 3, and there's that idea of, can I write this number underneath as a perfect square? I can. 4 times 3, 4 is a perfect square. The square root of 4 is 2. Root 3 stays underneath, and it's plus or minus. Okay, so x equals plus or minus 2 root 3 in that case. Here we have 1/5 times the quantity x plus 3, that's all squared, equals 7. How do you get rid of that fraction, that 1/5? Well, if 1 divided by 5, multiply each side by 5, and I do that, and I get the quantity x plus 3 squared equals 35. To undo a square, you square root, and I do that to both sides, and I get x plus 3 equals plus or minus root 35. Remember, when you square a square root, they are gone. They cancel. They're inverses. They undo one another. So now the x plus 3 is free. You can get rid of that 3 now. So I subtract 3 from both sides. I get x equals negative 3 plus or minus root 35. Root 35 is not a perfect square, and it can't be written as a perfect square. You think 35 is 7 and 5. Neither one are perfect squares, so I actually just leave 35 under that radical. It can't be simplified. Okay? So if you have any questions or comments, you can go ahead and write them below. You can also email me at nicholas.bennett@dc.gov. Thanks, guys. We'll see you next time.